All right. So, hello everyone. So today, this is the sixth installment of the course entitled as Transition Metal Organometallic Chemistry: Its Principles to Applications. And this is Anubhav Nath. I am currently a PhD student in the Department of Chemistry at IIT Kanpur. So today, I am going to discuss about some basic concepts on one of the topics of this organometallic chemistry, which is named mainly as CH activation. And briefly, I would discuss some questions on CF activation, that's the carbon fluorine bond activation. And also, lastly, we'll discuss a bit about the Fischer carbene and the Schrock carbene complexes. And I have actually devised several questions so that by answering those questions, we will be able to clarify the doubts or the basic concepts. So we'll start. So the first question is regarding the cleavage of a CH bond during CH activation by transition metal involves which of these following options? Option 1 is the oxidative addition. Option 2 is the acoustic interaction. Option 3 is the reductive elimination. Or option 4 is the metal to ligand sigma donation. So correct options are, this is actually a multiple selective questions, not an MCQ. It's actually an MSQ. The correct options are oxidative addition and the acoustic interaction. So in some previous slides also I have discussed a bit about the acoustic interaction and also on oxidative addition. You know, at the CH bond is actually very much less polar, or we can say non-polar in nature, and that's why activation of CH bond, because the bond dissociation energy is also quite high for the CH bond, the activation can be done in presence of transition metal complexes, briefly abbreviated as TM. So if a transition metal is present in some X oxidation state plus X oxidation state and a CH bond is there, so if it's activating the CH bond, then the corresponding oxidation state of the transition metal will be plus 2. So it will be X plus 2. And the carbon and the hydrogen both will be negatively charged, and they will be bound to the transition metal in the mode alkyl group and the hydride group. So that is one of the major pathways by which a transition metal can activate a CH bond. The acoustic interaction is somewhat different. A acoustic interaction actually may lead to oxidative addition of the CH bond. When such a CH bond is present in the ligand framework, that's how the CH bond is actually very much proximal or close in nature to the transition metal. Then the transition metal actually has a several kind of interaction with the hydrogen, and also the bonded carbon atom will also have some interaction with the transition metal. So between the transition metal, the carbon and the hydrogen, they are forms a three center two electron bonds. That's why this is called an acoustic interaction. So with the help of what, the CH acidity increases, the CH bond strength actually decreases, and by several factors actually get hampered by the aid of acoustic interaction, as a result of which CH bond activation can take place by the oxidative addition pathway. Now, the metal to ligand sigma donation does not have a significant effect on the CH bond activation. It actually stabilizes the metal center when the extra electron density is shifted from the metal to the ligand atmosphere or the ligand construct. And in the case of reductive elimination, what happens? In the case of reductive elimination, two moieties are there actually. There can be alkyl groups, one may be alkyl, one may be halide group, one may be an alkyl group, other may be a hydride. So these two actually groups can actually combine and leave the metal in an oxidation state less than the present oxidation state. So it is actually the reverse of the oxidative addition reaction. Here in oxidative addition, a carbon hydrogen bond or any CX bond gets oxidatively added to the metal center. But in case of reductive elimination, these two CX bond or these two moieties get combined or they get adjoined, and the carbon center or the metal center, the transition metal center, actually comes down by oxidation state plus 2. So if a metal is present in oxidation state plus 2, by reductive elimination it will be coming to oxidation state 0, and reverse is true for the oxidative addition. If a metal or transition metal is actually residing in the state plus x, and by oxidative addition it will be going to plus x plus 2. So oxidative addition and the reductive elimination actually are two vice versa things, or just two opposite things. So the correct options are oxidative addition and the acoustic interaction, which are actually mainly involved for the activation of the CH bond by a transition metal. Now we will come to question number 2. So the question number 2 is regarding the application of the CH bond. Which are the applications of the CH bond? Since you can have a note that this question is devised such that the question is either is or are, so this can be an MSQ type of question or it can be an MCQ. So the question is as such. So these are which are the applications of CH activation? Firstly, the alkane functionalization. Second option is the disintegration of alkanes to carbon dioxide and water. Third option is the nitrogen fixations, and the fourth option is the redox reaction. So the cost that the main one of the main protocols. That's why the alkenes are actually nothing but hydrocarbons, straight chain hydrocarbons, which do not have any kind of unsaturation inside the moiety or motif. So the alkenes are actually very much less reactive in nature, because the CH bonds are actually very much stable because of the comparative size orbital overlap between the two atoms. That's why the alkanes are very much stable and actually inert. And that's why if we can have some pathways to activate the CH bond, then the alkanes can be functionalized. Functionalization means we have to put some groups into the alkane motif. The groups can be bromo, it can be alcohol or OH group, it can be a carboxylic acid moiety or any such kind of things, or an acetamide moiety. So any kind of moieties are there that can be called as functionalization of the alkane. CONH2, COCl, Br or F or Cl or OH, or cyanide or Cn or Nc, every such kind of functional groups are actually, when attached to alkane, are called as alkane functionalization. So the application of CH activation is nothing but the functionalization of alkanes, so that we can have a library of compounds via which we can actually go to different direction. We can produce several kind of commercially available reagents for our uses. The third question is the active. Which of the following bonds is the most challenging one to activate? Actually, in chemistry, we deal with several kind of bonds actually that can be activated in presence of certain metal complexes or other photolytic activities or other such reagents. But the question is, which of these following four bonds is the most challenging one to activate? The first option is the HH bond. The second option is the carbon hydrogen bond. Third option is the CC bond, and the fourth option is the carbon fluorine bond. Now, the correct option is the option 4, that is the carbon fluorine bond. So one by one we will discuss how we are getting the answer why CF bond is the most challenging one bond to get activated. So HH bond. So HH and CC. Let's come to the HH and CC bond at first. These are actually homonuclear bonds among all the options, and CH and CF bonds are heteronuclear in action. Now, these HH and CC bonds are seen homonuclear in nature, and these are actually overlap between two s orbitals or two p orbitals. That's why these bonds are actually very much strong in nature, and because of that, this bond dissociation energies lies in the range around 100 kilocalorie per mole inverse. That's why these bonds are actually very much tough to get activated. But here comes this C and CH and the CF bonds. You know that the fluorine is the most electronegative element in the periodic table, and that's why the CF bond possesses a severe ionic character in nature, because the electronegativity difference between carbon and fluorine is quite high. That's why these CF bonds are actually ionic in nature. So here I have actually depicted some of the points by the virtue of which you can have a grip on the concept of bond reducing energy, or the concept of activation of bonds. Now you can see that's the high electronegativity of fluorine. It is actually 4.0 in the Pauling scale versus 2.5 for a normal sp3 carbon. So this gives this CF bond a significant polarity or the dipole moment. So dipole moment, you all know or heard about it. Dipole moment is the charge separation, that is actually the distance between the two atoms multiplied by the difference in the charges between the two entities. Here the two entities are carbon and fluorine. Now, because fluorine is the most electronegative atom in the periodic table, that's why it causes significant del positive charge on the carbon atom, and it drags the electron density upon itself. That's why this CF bond is very much polar in nature, because it has significant amount of dipole moment. That's why this attraction between the carbon and fluorine is very much unique in nature. That's why that's the very much unusual bond strength is actually attributed to carbon fluorine bond. That's why this CF bond is termed as one of the strongest ones in the organic chemistry platform. Look, in inorganic chemistry you can see there are metal halogen bonds that are very much stable in nature, because for example the sodium fluoride has a very much high melting point, because the difference of electronegativity between sodium and fluorine is quite high. But that is an inorganic compound. In organic chemistry world, or the universe of the organic chemistry, this carbon fluorine bond possesses the difference most in between the electronegativity factor between the carbon and the fluorine. That's why the most polar or ionic bond in organic chemistry is the CF bond. Now here in the last paragraph I have actually stated several kind of bond utilization energies. The CF bond is higher than other carbon halogen and carbon hydrogen bonds. The bond utilization energies of the CX bond within the CH3X molecule, where X is actually attributed to any halogens or hydrogen. Here you can see, for in case of X equal to fluorine, the CX bond use energy is 115 kilocalorie per mole. In case of Cl, the energy is actually dropped by 10 kilocalorie per mole, that is almost 42 kilojoule per mole. So from shifting from fluorine to chlorine, actually from going to CH3F, that is the methyl fluoride, to going to methyl chloride, that is the CH3Cl moiety, the bond reduction energy is actually getting disrupted or decreased by an amount of 42 kilojoule per mole. That is quite a high number. And here you can see when X is actually, in case of hydrogen it is 105. So from fluorine to hydrogen the bond reduction energy is dropping by 42 kilojoule per mole. Here you can put an argument like why, in despite being electronegativity difference or no electronic difference between the carbon and hydrogen, this CH bond is this much of stability. The answer lies within the orbital overlap. Here you can have a note that carbon and hydrogen both are actually having their s orbitals, and they are actually having the principal quantum number in the same range. That's why the orbital overlap is quite strong in case of CH bond. The covalent bond is actually very much strong in nature. In case of Cl, Br, iodine, they are actually having these 3s 3p 4s 4p kind of orbitals. They are actually quite large in nature, which are having a several orbital mismatch with the 2p or 2s orbital of the carbon. And because of the orbital mismatch, the bond uses energy of the carbon Cl or the carbon bromine or the carbon iodine bonds are quite low. Here you can see this 83.7 kilocalorie per mole is for chlorine, the 72.1 kilocalorie per mole is for bromine, and for iodine it is 57.6 kilocalorie per mole. That's why the carbon fluorine bonds is the most challenging bond to get activated in the field of organic chemistry. So here we will drop to question number 4. It is actually regarding the perfluoroalkyl metal complexes. The question is as such: the RFM complexes, where RF is the perfluoroalkyl group. The perfluoroalkyl group, actually I have stated in some previous slide or previous discussions what are actually perfluoroalkyl groups. These groups are nothing but C6F5 or CF3 groups or CF2CF3 groups or CH2CF3 groups. So any alkyl group which possesses more than one fluorine atoms inside it, it is called the perfluoroalkyl group. The perfluoroalkyl group metal complexes are really stable owing to which of the following options: there can be multiple options. Options are MC overlap increased as a result of contracted metal orbitals arising from higher partial charge on metal. MC overlap decreases as a result of contracted metal orbitals arising from higher partial charge on metal. The third option is the lower energy pi star molecular orbital of RF facilitates the metal to RF back bonding, or the higher energy of the pi star MO of the RF that is actually facilitating the metal to RF back bonding. So the option 1 and option 3 are correct, which is actually the MC. Let's discuss about the option 1, that is the MC overlap increases as a result of contracted M orbitals arising from higher partial charge on metal. So let's come from the basics. Here you can see that is the carbon is actually attached to several fluorine atoms, that is the perfluoroalkyl groups, and because of the group electronegativity of the perfluoroalkyl group is quite high, that's why the electronegativity of these CFC groups are quite high in nature. That's why the metal develops several positive charge on its head. That's why the metals orbitals actually having a higher partial charge on the metal. That's why, because the effective electronegativity or the effective electronegativity of the metal orbital also gets increased, because the effective nuclear charge, or you can say in the status via the aid of status rule, that is the effective nuclear charge, or the Z star, or abbreviated as Z effective, is actually quite high in case of metal orbitals when it is bonded to perfluoroalkyl groups. That's why because of the several actually increment in the effective nuclear charge on the metal nucleus, the orbitals gets contracted, because it actually pulls or drags the outermost orbitals of the metal center. That's why the metal and the carbon, the difference in energy between the metal and the carbon of the perfluoroalkyl group actually comes closer in nature, because the overlap energy also gets severely enhanced. That's why the RF bond is actually quite stable in nature, and that's why the shape complexes are quite stable. Another factor is arising, that is depicted in option number 3, that is the lower energy pi star MO of the RF is actually facilitating the metal to RF back bonding. In case of metal carbon bonds, I have actually discussed, the metal is actually throwing its electron density on the sigma star orbital or the pi star or any of the suitable orbitals on the carbon center. Here you can see that is the because of the electronegativity, high electronegativity of the RF, the MO or the pi star MO of the RF actually gets stabilized. That's why the metal, it is easy for the metal to throw the extra electron density to the RF in a quite facile manner. That's why the back bonding is also gets enhanced, because the direct bonding from the ligand to metal is actually quite high, and the back bonding is also quite high, because these two factors are synergic in nature and they are cooperative also. That's why the RFM complexes are quite stable. Now we will come to question number 5. So it is the cis orientation of the ligands is required for the reactions. First option is the oxidative addition. The second option is the reductive elimination. The third option is the migratory insertion, and the last option is the beta hydride transfer. So, firstly, which of the following options is correct? So, the options 2 and 3 are correct, where reductive elimination and the migratory insertion. So, one by one, we will discuss how these are actually taking place and why these specific processes demand the cis orientation of the ligands. Now, for oxidative addition, we don't need any kind of orientation of the ligand. For oxidative addition, we just need a bond that can be actually added oxidatively across the metal center. It can be a CH bond, it can be an CX bond where X is a bromo or chloro or iodo or any kind of such things. So for oxidative addition, we do not need any kind of orientation of the ligands. In case of beta hydride transfer also, in the hydride, that is the beta hydride that is actually bonded to the beta carbon atom, that should be close or proximal in nature to the transition metal. That is also not demanding the cis orientation of the ligands. But in case of reductive elimination, the cis orientation is actually quite demanding, because in case of reductive elimination, that is actually the opposite of the oxidative addition. The two moieties should come to in close proximity or in the cis orientation to get eliminated reductively from the transition metal center. So if they are actually residing in a trans manner or anti to one another, then their reduction or elimination is not possible at all. That's why for reductive elimination, the cis orientation of the fragments of the moiety is actually required. In case of migratory insertions, also a group that is a methyl group, for example, let's say a methyl group or a phenyl group, is actually shifting its position to the corresponding CO, that is the carbonyl moiety. So if it is present in the trans or the anti manner, then the distance that it needs to cover is actually quite high. But when it is actually cis or in some 90-degree angle with the other motif, that is the CO moiety, then it's shifting from the methyl, that is methyl shifting of the methyl or the phenyl group to the just beside the in 90-degree orientation to the CO is actually quite facile nature. That's why the reductive elimination and the migratory insertion, these two pathways are actually demanding the cis orientation of the ligands. Now we'll come to question number 6, which is the regarding the reversal of polarity regarding which or ampulang. So in previous slide I have actually stated which is actually ampulang or which is termed as the reversal of polarity. So we know that is what is actually the accordingly the most accepted electronegativity issue of the periodic table elements. We know that is the methyl groups are actually electropositive, so they develop del plus charge on themselves, and the halogens are electronegative, so they will develop del negative charge or partial negative charge on their head. So whenever in which of the cases when this case of polarity will be reversed, because the carbon containing moiety will be acting as an electronegative element and the halogen moiety will be acting as an electropositive element, then we can say this is ampulang or the reversal of polarity. So the options are methyl chloride CH3Cl, methyl iodide, that is CH3I, CF3Cl, that is the trifluoromethyl chloride, and lastly CF3I. Here that is the methyl group and the CF3 group. Methyl groups have group electronegativity in the range 2.2 to 2.6, and CF3 group has a group electronegativity in the range 3.8. That is quite high compared to the normal methyl group. So in case of the other part of the question, it is the chloro or iodo. Chlorine is having a electronegativity in the Pauling scale as 3.0, and iodine has an electronegativity 2.3 to 2.5. Now, in case of CF3I, you see that the CF3 has a group electronegativity that is 3.8, and iodine has a electronegativity in the Pauling scale as 2.4. So the electronegativity difference is actually quite high in the most one in all of between all of the four options. In case of other options, you see the electronegativity difference is not that much high. In case of this, it is 2.5 and chloro is 3.0. It is 2.5, it is also 2.5. So there is actually not enough electronegativity difference between the two fragments. In case of CF3Cl also, CF3 has an electronegativity 3.8 and Cl has an electronegativity 3.0. So here in this case, CF3I, the electronegativity difference is the highest, which is actually almost 3.8 minus 2.5. That is almost 1.3 unit difference in the electronegativity. And unlike the normalized statements of the methyl iodide, this CF3 is actually having a del negative charge on it, and the iodine is having a several positive charge on it, because iodine is actually more electropositive in nature than CF3 group. That's why in case of CF3, instead of writing del positive on carbon and del negative on iodine, we will write del negative on carbon and del positive as on iodine. Here you can see clearly distinguish between CH3Cl and CF3I. Look, in case of CH3Cl, the CH3 is having a del plus charge and Cl is having a del negative charge, because CH3 has an electronegativity 2.5 and Cl has an electronegativity 3.0. That's why the chlorine is actually more electronegative in nature, so it will drag the electron density of the CCl bond on itself actually. But in case of CF3I, the iodine is actually electropositive and CF3 is acting as the electronegative element. That's why the carbon CF3 is actually is behaving as a del minus unit, and iodine is actually dealing itself as a del positive unit. So that's why in case of CF3I, the reversal of polarity or the ampulang comes into picture. So let's come to the question number 7. It is regarding the metal to ligand pi back donation is least in case of which of the following options. First one is the metal carbonyl complexes. Second option is the metal alkyl complexes. The third option is the metal carbene complexes of Fischer type, and the fourth option is the metal alkene complexes. So the correct option is option two, that is the metal alkyl complexes. So now we will discuss why it is so. Why in case of metal alkyl complexes, the metal to ligand pi back donation is least. Ligands that, firstly we will have to think of, or have to have a discussion on which ligands are actually capable of acting as a pi acceptor ligand, or popularly known as pi acidic ligands. So ligands which are having actually the empty or vacant orbitals, they can be p orbitals or there can be s or d orbitals depending on the structural framework of the ligand. So ligands which are having these empty or vacant orbitals, which are actually able to interact with the metal d orbitals for the formation of pi bond, are actually called these pi acceptor ligands, because these ligands are actually capable of eating the or engulfing the electron density from the metal's d orbitals. That is when the metal is having a higher electron density on itself. Now these ligands actually possess a vacant carbon, which can be a vacant pi star antibonding molecular orbital or an empty d orbital, depending on which the metal will be able to push the electron density. Now, when these ligands are actually bonding with the metal, the d orbital, metal d orbital is donating its electron density to the empty orbital of the ligands. That's why this type of bonding is called as the pi back donation or pi back bonding. So one by one, we'll discuss which kind of ligands are actually capable of doing this pi back bonding in nature. So here, among all the four options, we have four kind of ligands. First one is the carbonyl, that is the CO. Second is the alkyl, that is any R group. It can be CH3 or CF3 or a phenyl group or a neopentyl group, or as such. The third option is the carbene complexes of Fischer type, and the last option is the alkene complexes. Now, in case of alkene, there are actually pi star orbitals. The alkene is actually bonding a pi and pi star, and the pi stars are actually vacant. That is the LUMO of the alkene. And on the LUMO of the alkene, the metal, when it is having an extra electron density on itself, it will push electron density on the pi star LUMO of the alkene. In case of carbene also, it is in case of Fischer type of carbene, the development of the p orbital on the carbon center is actually vacant, and that is actually able to drag the electron density of the metal center to its head, and that's why the metal's electron density gets decreased. That is the way of pi back donation in case of carbene. The carbonyl complexes are the most popular ones in this case, because the oxygen is having a high electronegativity in nature, and that's why the on the pi star LUMO of the carbonyl, the metal is actually able to donate its extra electron density. But in case of alkyl group, that is the any R group, that is any CH3 or neopentyl group or sec butyl group or any CF3 group, they are actually entirely bonded by sigma bonds. No kind of presence of pi bond is actually seen in case of alkyl groups. So that's why the alkyl groups are devoid of any kind of vacant d orbitals or any kind of pi star antibonding molecular orbital. That's why they are actually only having these sigma star orbitals. Now the sigma star orbitals, you all know, are quite high energy in nature. That's why pushing the electron density of the metal to the sigma star, that is quite high in nature, is not that much prominent in case of metal alkyl complexes. That's why we need actually development of several alkyl group which are having some electronegative atoms attached to itself, that on a virtue of which the electron density will be shifting from the metal center to the ligand center, because the ligands are having actually high energy sigma star antibonding orbitals. So if we are having a fluorinated alkyl group or the perfluoroalkyl groups, then the extra electron density, then the orbital energy will drop down and it will be close in proximity with the metal orbitals. Then the metal will be able to push its extra electron to the ligand framework, and that's why in case of these metal alkyl complexes, the metal to ligand pi donation is the least, but where in case of metal carbonyl complexes, the metal to ligand pi back donation is the most favorable one. So here actually after discussing a lot on the CH activation or the CF bond activation, or depending upon the bond strength of all the bond dissociation energies of the CH, HH or CF bond, now let's come to a practice problem solving questions where you would have to understand the catalytic cycle, how this kind of CF activation is taking place. So the first question is regarding the CF activation, where the question is the hexafluorobenzene is treated with hydrogen pressure at 95 degrees Celsius under 6 bar of pressure, and the catalyst is actually this Me3P whole 4 rhodium hydride. So it is a rhodium 1 compound, you can see, and rhodium 1 is actually D8 in system, and we are having 4 PME3 group, because the 4 PME3 group, all the PME3 groups are 2 electron donors, so they are actually 8 electron donors. So 8 plus 8 is 16, and hydride is a 2 electron donor, so it is 18. So this is an 18 electron hydride complex. This is acting as a catalyst in this context. And now what is the product? So the product is activation of the CF bond of this hexafluorobenzene moiety. The product is this one, where one of the fluorine group is not present, that is the pentafluorobenzene. One of the fluorine atoms is actually substituted by hydrogen atom, and the other product byproduct is the ET3NHF, that is a salt, tetraethyl ammonium fluoride salt. So let's come to a reaction mechanism, how the formation of the C6F5 moiety is taking place. Now this is the proposed mechanism how the CF bond gets activated. So here the catalytic cycle will be starting. You see, this is the nothing, I have actually abbreviated the PME3 group as the L. So L4R4 L4RHH, rhodium hydride moiety. So here the one of the ligand dissociation reaction is taking place. Since this L or PME3 is a neutral ligand, in the first step ligand dissociation takes place. So from 18 electron system, it is actually going to the 16 electron system. The 16 electron system is now this is the L3RHH. This is the now when what happens? This is ET3N is actually a base, and ET3N is actually a base, and this C6F5 is there. Now what happens in this case? C6F5 actually ET3N is actually going, and ET3N is actually abstracting this proton. So ET3N is actually base is there. Now base, in case of this case, this hexafluorobenzene is present, and in case of base, this fluoride actually gets eliminated because it attracts on one of the carbon atoms of the C6F6. Now the base gets regenerated, and this the H is actually getting bound to the F atom of the this H is actually coming from this hydride of the rhodium. So that's why HF is one of the byproduct. Now base and HF, base is actually, it is a base, that is the ET3N, and HF is an acid. So acid and base, what happens when acid and base are combined is actually producing a salt. So that's why it is the ET3N HF salt. So from C6F6, by the aid of the hydride's attack on the fluorine atom, the elimination of fluorine atom takes place. The C6F5 group gets bonded to the rhodium center. You see, this C6F5 mononegative anion is actually quite stable in nature, because the 5 fluorine atoms by the virtue of their severe electron withdrawing electron withdrawing inductive effect or minus I effect, the group is stabilized. So C6F5 is actually bonded to the rhodium. Now they are actually putting severe hydrogen pressure, that is a 6 bar pressure. Now this hydrogen pressure, you know, that is the oxidative addition is going to take place, because this rhodium is actually present in the oxidation state 1. Rhodium is present in oxidation state 1, and when hydrogen is actually pushed in the reaction medium, since hydrogen is dihydrogen is as a non-polar moiety, and I have actually discussed in the previous slides that non-polar moieties gets hydrogenated or gets oxidatively added to the metal center in cis orientation, not in the trans orientation. So hydrogen moiety is actually going to this rhodium as a cis orientation, and we are producing this cis dihydride rhodium intermediate, which is having a perfluoroalkyl group present. Now what happens? The C6F5 and the hydrogen is actually gets reductively eliminated by producing this C6F5H moiety, and we are having this catalytically active species back. So here I'll again or I'll repeat the statement how this taking place. Firstly, the ligand negotiation takes place. Firstly, a ligand takes place to form the 16 electron complex. Then, in presence of base, this C6F5, this hydride moiety is actually taking one of the fluorine atoms of this C6F6, and now this HF is actually getting eliminated in presence of base as a salt. So this C6F5 is actually now bonded to the rhodium center. Now, in presence of hydrogen, it is actually a low valent metal. Low valent metals are actually very much prone towards the oxidative addition pathways. So this rhodium is actually gets oxidatively, hydrogen gets oxidatively added to the rhodium center. The rhodium center, and this rhodium is actually producing this cis dihydrate intermediate. Now these two cis motifs are actually gets reductively eliminated in presence of the other moieties, and reductively elimination, and we are having the catalytic active species back. Yeah. Now the ninth question is the give some routes for the synthesis of transitional metal alkyne complexes. So here we are actually going to discuss about the transitional metal alkyne complexes. Here you will see, there are actually transition metal. Here I will discuss about several examples where you will have some transition metal, that is the TM alkynyl complexes. So now these are the three examples I have picked up where you can have an idea about how these transition metal alkynyl complexes are prepared. So alkenes are this one where a double bond is present. So these will actually be bonded to the transition metal center. Here you can see in all the three examples a transition metal, that is in case of this iron, in this case it is also iron, in case it is platinum, is actually bonded to alkene groups. That is the alkene. Here is the alkene and this is the alkene here. So in the first case, what happens when in case of this eta 2 bonded acetylene moieties bound to the transition metal center is treated with a HCl at a low temperature, then these transition metal alkyl complexes are formed. What happens in this case? You can see that is the phosphonium bond. This is the phosphine bonded platinum center, which is having a eta 2 donation from this alkene group. Now, what happens in this HCl? One of the protons is actually now hydrogenating. It is alkyne group, and it is from alkyne is going to the alkene group. Now this carbon is actually possessing a several negative charge on it. That's why it is now bonded to the platinum center. And this chloride moiety is, since because it is electronegative in nature, it will be bonded to the 3THCl center. It is nothing but a sort of oxidative addition of the HCl bond across this platinum carbon bond. In the second example, we're having a CpFe moiety, that is a cyclopentadiene Fe ferrocene kind of moiety, which is actually again bonded to then dimethyl acetylene. That is the dimethyl acetylene moiety, and a phosphine is also there. So what happens when it's treated with this lithium 2 CuCN pH2 salt? So in this case also you can see that is this actually behaving as a this phenyl group. Actually this is actually a nucleophile in nature, because you see this lithium is electropositive in nature, and so this entire moiety is electro. You can see this is an electropositive moiety and this is an electronegative moiety, because lithium is an S block electropositive metal. So there possesses several negative charge on this moiety. Now among all these fragments, copper or cyanide or phenyl, this phenyl actually on because of the least electronegativity in nature, this actually is having the negative charge on it. So this phenyl moiety will attack on one of the carbon atoms here on this acetylene moiety. Because these two acetylene carbon atoms are equivalent in nature, so it will be bound to it will be attacking on any of the carbon center. So there will be possessing a negative charge on the other carbon. So this other carbon will be now bonded to the iron atom. So that's why in case of this this positive charge is there, so there must be a negative charge moiety, that there can be OTF, or this can be PF6, or this can be a halide. So this halide and this lithium atom will be eliminated as a lithium X salt, and this pH moiety will be attacking on this carbon, and this carbon, on account of having a negative charge, will be bonded to the iron center. That's how this alkynyl iron complex is prepared. Let's come to last example of this transitional metal alkynyl complex, that is the iron nonacarbonyl will be treated with this 1,2-dibromoethylene. So what happens when these two compounds are treated with one another? What happens in this case? There is an iron bond. So this iron bond will not be eliminated or not be ruptured actually. But since, because this bromine is actually there, and you all know that is halogen atoms can form a bridge between two atoms, this bromine is actually acting as a bridging ligand here between these two iron atoms. Now CO, this actually, there are actually 9 CO molecules. Here you can see in the product there are 6 CO molecules. So 3 CO molecules are actually eliminated in nature, eliminated. And what happens to the other thing? This, because this CBr bond is activated, and this bromine is actually now acting as a bridge between these two iron center, the other carbon is actually now bonded to one of the iron centers. So the double bond, that is the olefin group, is actually now actually having an interaction or bonded to the iron center. So this is actually an eta 2 kind of bonding with the iron, and we are having a bridge, the three-membered bridge between those two iron centers, where a bond between the iron centers is also present. So these are the actually several classic examples how we can prepare these transitional metal alkynyl complexes. The next question is regarding between TiCH3 whole 4 and TiPH whole 4. Which of this is actually more stable? TiCH3 whole 4 is more stable than TiPH whole 4. The second option is that TiCH3 whole 4 is less stable than TiPH whole 4. Both are actually stable at room temperature, or TiCH3 whole 4 has a beta hydrogen atom. You see, in case of carbon, this TiCH3 whole 4, the no beta carbon atom is present. So the option 4 cannot be correct in any of the following cases, because it is not having a beta carbon, so it is only one carbon is present. So this is alpha carbon in nature, so this cannot possess a beta hydrogen atom. Now the option 2 is the correct one, which is the TiCH3 whole 4 is least stable or less stable than TiPH whole 4. So here is the answer. I will discuss the points one by one. This is actually a aryl group. This is actually an alkyl group. So this is a classic example where a difference between transition metal alkyl group and the transition metal aryl group will be discussed. This phenyl is aryl and this methyl is the alkyl group. Now transition metal alkyl groups are actually less stable than the transition metal aryl groups. The answer is quite simple in nature. You see, the aryl groups are having carbon in sp2 hybridization, but the aryl alkyl groups are having carbon centers in sp3 hybridization. Now between sp3 and sp2 carbon atoms, sp3 carbon atoms are less electronegative in nature, but sp2 carbon atoms are actually electronegative in nature in more, because sp2 carbons are actually having 33% of s character, but sp3 carbon atoms are actually having only 25% of s character. That's why these phenyl groups are actually more electronegative than the methyl groups. That's why the electronegativity difference between titanium and the this alkyl or aryl group is actually more in case of TiPH, not in the case of TiCH3. So there happens a several ionic character, development of several ionic character in case of TiPH4 moiety, not in the case of TiCH3 moiety. That's why TiPH4 is more stable than the TiCH3 whole 4. That's why in the case I have actually stated that D, that is the dissociation energy of the metal pH bond, is 10% higher than the metal methyl bond. Since you can see there is actually only 8% electronegativity difference between the phenyl group and the alkyl group, so the bond dissociation energy is actually only 10% higher, only in case of this. So that this the difference, the actually stability difference between TiPH4 and TiCH3 is not that much huge in nature, but TiPH4 is slightly more stable than CiCH3. Here for information I have stated the fact that TiPH4 actually decomposes at only this 0 degrees Celsius, where TiMe4 actually, that is the tetramethyl titanium compound, is decomposition temperature is only minus 40 degrees Celsius. So it is actually heavily unstable in nature. The next option is the next question is the you have to actually give some roots for the synthesis of transition metal acetylide complexes. So in the previous example, I have actually shown you how these transition metal alkynyl complexes are prepared. Now we will discuss how these transition metal acetylide complexes are prepared. So I have picked up two examples here. Firstly is the most popular one, that is the oxidative addition. Here you can see this is a PDPPH3 whole 4 where palladium is in this zero oxidation state. Now it is treated with this alkene, it is RC triple bond CX. Now what happens when they are actually both combined? So what happens? You can see this CX bond is there, and now I have actually told or discussed in the previous examples, these CX bonds are actually very much prone towards oxidative addition. Now this palladium is actually in its zero oxidation state, so low valence metal complexes are very much prone because they are having high electron density, so that's why they are prone to oxidatively get added. Now what happens with a concomitant dissociation of the ligand, that is the PPH3 triphenyl phosphine, this CX moiety gets oxidatively added to the palladium center. So we are having this complex from palladium 0, we are going to palladium 2 because in oxidative addition, plus 2 oxidation states are actually seen. PD2X, we are having this C triple bond Cr, that is the acetylide moiety. So that's why it is an acetylide transition metal palladium complex, and these PPH3 groups are actually present to fulfill the electron count of the metal center. This X can be Cl or Br or I. Since these Ci bonds are actually least stable in nature, so they are actually most reactive ones in case of oxidative addition. And the CF or CCl bonds are actually having high dissociation energy. That's why the CCl compounds are actually least facile towards oxidative addition. The second option is the nucleophilic substitution. So here you can see we are having this CpFeCO whole 2 iodine complex. This is an iron complex, that is the iron having oxidation state plus 2. Now this is treated with this Me3CN, C triple bond C, C triple bond CH moiety in presence of palladium MECN whole 2 Cl2. What happens in this case? You see this tannic, that is tin, as having a high affinity towards this halogen, that is the iodine. So it will abstract the iodine and it will be eliminated as Me3SNI. Now what will be happening now towards the this center? This iron center will be bonded to the carbon center, and it is actually an iron acetylide complex where two acetylide moieties are present. Now, what happens in this case? They're actually treating it with its N-butyl lithium. This N-butyl lithium is there. N-butyl lithium will be abstracting, is a very strong base. So it will be abstracting the acidic proton of this acetylide moiety. So it will be eliminated as butane, and we are having the corresponding salt. That is the FeCp CO whole 2 C triple bond C C triple bond C Cli. Now this carbon is having a several electronegative charge or the negative charge density on it because it is acting as a nucleophile. Now CpCO whole 3 MOCl. This is another moiety where it is a molybdenum complex when a CpCO3 COCl is there. Now this carbon minus the negatively charged carbon, that is the carbon anion type of center, will be attacking on the molybdenum center. So to eliminate the Cl minus by the aid of this lithium Cl, that's a LiCl salt. So this LiCl will be eliminated and this carbon will be bonded to the molybdenum. So that's how we can present or we can prepare the transition metal diacetylide complexes where two of the nucleus are different. One is the iron, another is the molybdenum. The next question is regarding a brief on the Fischer carbene complexes. So, for your information, I will tell you there's an in NAC, that is the in heterocyclic carbene complexes are classified popularly between two things. One is the Fischer carbene, another is the Schrock carbene. You have actually heard of it. So, here in the upcoming two slides, I will be discussing one on the Fischer carbene and other will be the Schrock carbene. And in the later sessions, I will be discussing several problems on Fischer carbenes and Schrock carbenes. So Fischer carbenes are what? This is the simplified view actually shown. Is a metal center will be bonded to the carbon, and this carbon is actually bonded to heteroatoms in nature. So this heteroatom, you can see this is X. X can be oxygen or sulfur or nitrogen. That's why, because the heteroatoms are there, this carbon will be bearing del negative or del positive or the positive charge, and the metal atom will be bonded to several electron withdrawing substances. So the metal atom will be having this del negative charge or the higher electron density. Now, because of the high electron density on the metal center, it will be now again this X will push its electron density on this bond, and metal atom will be having high electron density. This high electron density will again be pushed to the carbon center, and the heteroatom will be stabilized. That's why this heteroatom will be stabilized by the localization of the electrons in Fischer carbene. So in case of Fischer carbene, the carbon center is positive in charge. That's why it is electrophilic at carbon, and the metal center is bearing del negative charge. So it is nucleophilic at metal. So the most common synthesis feature of these Fischer carbene complexes is from the metal carbonyl compounds. So this is a classic CrCO whole 6 compound. When it is treated with alkyl lithium, there is RLi. RLi R minus will be attacking on the carbon, and we are having this acetylide moiety. This is Cr minus CO whole 5 RCO. This is the acetylide moiety. So the other resonance canonical is shown like this. This is a negative charge on the oxygen, and there's a bond between this chromium and the carbon, double bond. Now, if we put a hard alkyliding agent, that is the R2OTF or trimethoxy ammonium tetrafluoroborate, what happens? These oxygens will be alkylated. So we'll having this product CO5Cr double bond CrOR2. So this is actually the Fischer carbene complex we are talking about. If we are treating this compound with this acyl bromide, that is the CH3COBr, this O minus will attack on this carbon with concomitant release of the bromide ion. So it will be having this ester moiety, that is the OCOCH3. Now what happens? If we put this alcohol by the method of the hydrolysis, what happens? This R2 OR2 will be now treated with this OR2 will be attacking on this carbon, and by the elimination or addition elimination reaction by the aid of acyl halide will be again coming to this Fischer carbene complex. So this is the direct route. By the aid of hard alkali agent, we are actually from this hexacarbonyl system, we are going to this Fischer carbene, and this is the via route when we will first treat it with the acyl bromide, the CH3COBr, and then we will treat it with this alcohol, and then we will be preparing this Fischer carbene complex. The next question is regarding the Schrock carbene complexes. The Schrock carbenes are actually opposite in nature to that of the Fischer carbene complexes. So in case of Fischer carbene, I have told the carbon atom is actually having this del positive charge in nature. That's why they are actually bonded to the heteroatoms to stabilize that, and the metal atom is having the del negative charge. In case of Schrock carbenes also, the nature is actually quite actually thus the opposite, because in this case the carbon atom is bearing this del negative charge, and this metal atom is having this del positive charge. Now what happens in this case? This metal atom is having this electron donating sigma or pi electron dense actually atoms, and this R1 or R2 are not having any heteroatom is present to or bonded to the carbon center, because they are actually del negative charge. So such molecules or such groups will be present which are actually capable of dragging the electron density from the carbon center. So there are two possible or famous pathways by which we can prepare these Schrock carbene complexes. First one is from the Petasis reagent. This CP2TiMe2 is called the Petasis reagent. This Petasis reagent, upon heating, what happens in this case, in presence of mild base, this abstraction of this alpha hydrogen takes place. Actually nothing but the alpha elimination, and this methyl molecule will now get eliminated as methane, and by alpha elimination we are having this CP2Ti double bond CH2. This is actually a Schrock carbene. In case of option 2, this is a step based reagent. Step based reagent is CP2Ti CH2Al Me2Cl, when Ti and aluminium, this titanium aluminium, are actually bonded or breached via CH2 as a methylene group or the chloride group. So what happens in this case? Whenever tape-based reagent actually is a precursor to the Schrock carbene complexes. Whenever tape-based reagent is treated with any strong base like ET3N, what happens? This NR3, that is the R3N, will be attacking on the aluminium center. This bond between this, the bond between this nitrogen and aluminum is actually quite strong, because aluminum is electropositive metal and p block element, and nitrogen is electronegative. So nitrogen will attack on the aluminum. This bond between this carbon and aluminum gets ruptured, and bond between this titanium and CH2 gets formed, and this chloride will be eliminated in the form of AlMe2Cl, that is a salt, organometallic salt, and ArMe3 will be attacking on the aluminum. So that's why they are actually getting this Cp2Ti double bond CH2. This is the shock carbene. So here you can, I actually abbreviated these two famous compounds that are actually Grubbs catalyst and the shock catalyst. Both are actually examples of this shock carbene. Here in case of Grubbs catalyst, ruthenium double bond C is actually present, where two ancillary ligands are PCY3 and chloride. And in case of shock catalyst also, this molybdenum actually bonded to this OCMeCF3 whole 2, and also this bond between this nitrogen and molybdenum is taking place, and the carbon atom is having this that's an electron neutral substituent, that is the CMe2PH. So these shock carbene complexes are actually also quite evident in nature. Remember, there is the feature carbene and the shock carbene complexes are opposite in nature. Just in case of feature carbene complexes, the carbon is bearing del positive charge and the metal is bearing del negative charge, and just the reverse is true in case of the shock carbene complexes. The metal atom is actually bearing del positive charge, and the carbon atom is actually having del negative charge. So with this I will end my session, and now it is actually going to the your question answer part. So you can actually go ahead, you can ask questions on any of the any of the queries, you on any of the slides, if you can ask. This acoustic interaction is nothing but the interaction between the transition metal that we are dealing with the hydrogen or the carbon hydrogen bond transition metal. So you see, when in this case, by the aid of example, we can actually see here, you can see this titanium is actually getting bonded to the carbon center. So here, if we are having a suitably oriented hydrogen atom here, and this hydrogen atom is actually close in proximity with the metal center, then there would be an interaction between the titanium and the hydrogen, that will be putting the CH bond in some lower bond in the labile mode, and there will be happening significant amount of negative charge on the hydrogen atom. So there forms a three center two electron bond between the metal, the hydrogen, and the carbon by the aid of acoustic interaction. By the mode of acoustic interaction, the bond actually gets activated, the CH bond, and by virtue of which we can perform homogeneous catalysis or heterogeneous catalysis. So in case of this olefin polymerase, and that is a Ziegler-Natta polymerase, and you can have a note, this titanium complexes are actually performing this CH activation by the aid of acoustic interaction. So when a CH bond will be close in proximity with the transition metal, there will be a three center two electron bond formation between the titanium and the carbon and the hydrogen. So that is called the acoustic interaction, that will actually be useful to activate the CH bond.